Here are some notes on topic 8.1, energy degradation and power generation. These notes correspond to the first few pages of SOCO's chapter 7.1, so it might be a good idea to have your SOCO's book out while you watch this. If you take a look at the IB Physics Guide for topic 8.1, you can see there are 4 subtopics. Topic 8.1.1 says, state that thermal energy may be completely converted to work in a single process, but that continuous conversion of this energy into work requires a cyclical process and the transfer of some energy from the system. This is just a way of saying that in something like an automobile engine, work is done in cycles. You have a piston that goes up and down. A certain amount of work is extracted in each cycle of the piston going up and down. And if you want continuous work, that has to happen over and over again. We'll review heat engines a little bit in the next slide. The next subtopic, 8.1.2, asks that you explain what is meant by degraded energy. So we'll be talking about what energy degradation is. And subtopic 8.1.3 talks about sand key diagrams. And we'll look at a sand key diagram, in fact 2 of them, and help you understand what they are all about. And finally, topic 8.1.4 says outline the principal mechanisms involved in the production of electrical power, and we'll talk about that a little bit. We've talked about heat engines before. Heat engines would be things like automobile engines, steam turbines, old-fashioned steam locomotives. And remember that heat flows naturally from a high temperature place to a low temperature place. And if we're clever, we can take advantage of this and design a device that will extract work from this process. Kind of like as a ball rolls downhill, if we're clever, we could design a device that would extract some work from that change in potential energy. The bigger the temperature difference between the high temperature reservoir and the low temperature sink, the greater the efficiency of the heat engine. So again, the bigger the temperature difference, the better this works. The trouble is, as heat flows from the high temperature area to the low temperature area, the temperatures are going to tend to become, have a smaller and smaller difference. They'll tend to equalize. And as the temperatures get closer and closer together, the efficiency of the heat engine goes down. The amount of work we can extract goes down. Now eventually we reach a point where the temperatures are equal and we can no longer extract work at all because heat doesn't flow from the one spot to the other. Now the total amount of energy is still the same as we had before, but we say the energy has been degraded. The efficiency of a device is equal to the power that comes out of the device divided by the power that goes in, and the efficiency can be expressed as a fraction, but it's often converted to a percent. So if the amount of power coming out of the device is the same as the amount of power going in, then the efficiency will be 1 or 100%. In most devices, heat engines for example, more power goes in than comes out, so the efficiency is always less than 100%. So let's summarize. A heat engine is a device that can extract useful work from heat moving from a high temperature location to a lower temperature location. And as that flow occurs, the temperature tends to equalize, and therefore the difference in temperature becomes smaller and smaller, and eventually we can no longer do useful work. So even though energy being conserved, the same amount of energy is present, it becomes less useful. We need a temperature difference in order to extract work. And when we have this energy that's at a lower state, in that we can't get work from it, we say that the energy has become degraded. So that's what we mean by energy degradation. The energy becomes less and less useful because we cannot extract work from it. The next subtopic in this section is sand key diagrams. And a sand key diagram is a visual representation of the flow of energy. So if you take a look at this picture, the energy we start with, of course, is 100%, and this is the energy loss in a gasoline internal combustion engine, as you can tell from the title. And of the 100% of energy that we start with, that will be the gasoline in the end that goes into the engine. Only 25% of it makes the car go down the road. That's the green arrow that's labeled 25% effective power. 5% of the energy is used in overcoming friction and losses in the engine and drivetrain. So we get a smaller, a much skinnier arrow representing 5%. Ideally, the thickness of that 5% arrow should be 5/100ths or 1/20th of the thickness of the original yellow arrow coming from the left. 30% of the energy goes into heating the coolant, so we have an arrow that's 30% as wide as the original, and 40% comes out of the engine as exhaust heat, and that arrow should be 40% as wide. So again, the idea of a Sankey diagram, it's a way to kind of visually show where energy goes. The fatter the arrow, the larger the percentage of the energy is going in that particular direction. Here's a much simpler Sankey diagram. This is probably representing the energy flow in an incandescent light bulb. So if we start with 100 joules of electrical energy in the left there, you'll see that only 10 joules or 10% of the energy gets turned into light, and 90 joules or 90% of the energy, the big fat arrow, gets turned into heat. And generally speaking, in a Sankey diagram, the arrow that continues to the right, the one that doesn't curve off, is the direction that we actually want the energy to go. Here's a block diagram that covers how most power generating stations work. In most situations, you have a source of heat, and that source of heat could be burning coal, burning natural gas, burning oil. It could be the heat from as a byproduct of the fission reaction from the decay of uranium. But in any case, you have heat, which is used to boil water. The water turns to steam. When water turns to steam, its volume goes up by a factor of 1,800 times, and the steam is then routed through a turbine. And a turbine is just a fancy fan which spins like a pinwheel when the steam goes through it. And the steam turning the turbine blades will rotate a shaft, and that shaft is connected to a generator. And in the generator, you have coils of wire being rotated in a magnetic field, which by Faraday's law of electromagnetic induction is going to produce an electric current. That current then the voltage is then stepped up by a transformer, goes through transmission lines, and gets to your house. That's a very simplified version of what happens. If you have hydroelectric power, then you avoid step one, and you simply have falling water. The gravitational potential energy from falling water is used to spin turbine blades, and steps 2, 3, 4 are the same. That's it for topic 8.1. Tune in next week and we'll talk about topic 8.2.